This lab is to measure the numerical aperture of an optical fiber. The first thing we need to do is to prepare the end of the fiber so that it's flat and smooth. Take the fiber and remove a small piece as straight as possible, and then we're going to polish it using wet or dry paper or emery paper, 600 grit, very fine, and just do a few figure eights like this. The idea is to have a nice smooth edge, a nice smooth finish on the end of that fiber. Finally, we'll clean it with a little bit of alcohol on a lid-free wipe. Now that the end of the fiber is flat and clean, we need to couple laser light into the fiber. We do that with a helium neon laser from the kit on a tilt table. First, have the beam as straight and level as possible using the tilt mechanism, the tilt bolt to level the laser, and use the microscope objective in a microscope objective mount in order to bring the light to a focus. The far end of the fiber is located right at the focal point of the microscope objective. If the microscope objective and the fiber holder are both on bases, it makes the job a lot easier because you can adjust back and forth as well as up and down. To hold the fiber, we're using a slide holder from the kit. And you can see that the light is coupled into the fiber. There are a lot of different ways to measure the numerical aperture of the fiber, and we have two in this particular lab, and then I'll show you a third later. The first method is quite simple. It just involves looking at the cone of light that comes out of the fiber and measuring the cone angle. With the fiber taped to a piece of plain white paper, you can kind of wiggle the laser back and forth to get the largest cone of light. And then, using a straight edge, mark the limits of that cone on the paper. Then remove the fiber and use the protractor to measure the acceptance cone angle. And the numerical aperture is then calculated for 1/2 of that angle. The second method of measuring numerical aperture is a lot more finicky, but the results are quite a bit better. We need a laser, again, and a microscope objective to focus the laser light onto the end of the optical fiber. This is, again, plastic optical fiber. And the far end here, the output end, has been cleaved and polished as flat as we can. What we're going to do is we're going to take this fiber and rotate it so that this cone of light that is swept out will sweep past an optical detector. And the detector will read the intensity as that fiber rotates. That means the fiber has to be mounted exactly at the center of rotation of the rotational stage. One way to do that and keep the fiber from turning as it rotates is to mount a 2-inch post at the center of the stage and a 2-inch post at the edge of the stage. And the fiber will be taped across them like this, with the end right at the center of rotation. The detectors that come with the kit have an detector area that's really too large for this particular experiment. So what we'll do is cover the end of it with a piece of, in this case, duct tape. We'll use electrical tape, leaving a small space of, maybe 3-4 millimeters, and that will be the detector. The next step is a two-person job. What we want to do is to have the fiber aligned so that we get a maximum reading on the meter when the stage is reading 0 degrees. So what we can do is to loosen the post in the post holder and move the entire assembly up and down and back and forth while reading the meter, which, as I said, takes 2 hands or 2 people, until a maximum reading is reached, and then tighten it. All the while, the dial on the rotational stage is set at 0 degrees. So now I have maximum reading. I'm at the meter detector is at the brightest spot of that output pattern. Now it's just a matter of taking power readings every 10 degrees in one direction and in the other direction as we rotate the fiber around. So this cone of light is being swept back and forth. The good part about this, doing the lab this way, is that students will now make a graph of received power as a function of angle, and they'll get a nice curve, and then find, we'll take the 5% peak power points as defining the acceptance angle for the fiber. Here's another method of measuring the numerical aperture of a fiber. With the fiber still mounted on this platform, direct it towards a screen. If you measure the distance from the end of the fiber to the screen, and the diameter of the spot of light projected onto the screen, you can use trig to figure out what the acceptance angle is. So this is a good way for students who have some knowledge of trig. We can just take the distance to the screen and the radius of that spot and use the inverse tangent function to find out what the half angle is and calculate the numerical aperture from that. Notice as I move the fiber, the spot pattern changes. What's happening is, as the fiber geometry changes, modes are shifting from one mode to another in the fiber, converting from higher order to lower order. And we can see that in the displayed pattern on the screen.